Hi everyone, welcome to this talk. I'll be talking about our work Deterministic Approximation for the volume of the Truncated Fractional Matching Polytope, and this is joint work with Hung Guo. In this work, we study the volume estimation question. So here given our input is a convex body in high dimensions, and our goal is to estimate its volume. This is one of the most primitive tasks that human beings have performed. It's also a fundamental parameter for any convex body. So this problem has close connections to many important problems in analysis and geometry, and including the development of random walks. But exact computation of volume is a sharply hard problem. That's why we study algorithms that approximately compute the volume. Let's define the problem formally. So here our input is a convex body K, and we are also given an epsilon. And our goal is to output a 1 plus minus epsilon multiplicative approximation to the volume. So our running time should be polynomial in 1 over epsilon and also polynomial in the number of queries that we make to the body. So normally we are given access to a body in the membership oracle model. So that means that we have an oracle which on input a point in space, outputs whether the point is inside the body, or gives us a hyperplane separating the point and the body. So in this model, there exist polynomial time approximation algorithms. So this work was started by Dreyer, Fries, and Kannan. And crucially, these algorithms use counting to sampling reductions. And they work while they work for general bodies. They are all randomized algorithms. In recent times, there has been an explosion in deterministic counting algorithms. For example, we know algorithms that can count independent sets, matchings, colorings on bounded degree graphs, and in some cases, for example, counting independent sets on dense graphs, like dense random bipartite graphs. The techniques here are many. I'm just listing a few. So there's correlation decay, there's Barwin-Knox polynomial interpolation method, there's cluster expansion, there's local central limits theorems, and so on. So the question is, can deterministic algorithms approximate the volume? It turns out the answer is no. No for general convex bodies. And this is a classic result. It was proved by Elkes and Barani and Fioredi independently. It shows that deterministic algorithms must make exponentially many queries to the convex body. The one thing to note is that the hard instance here is an adaptively constructed union of convex balls, which still leaves the question open whether there exists polytime deterministic algorithms for convex bodies which are nicely represented. And for the context of this talk, nicely representable would mean polytopes. So we're given a convex region which is defined by linear inequalities. So as a sanity check, we can see that this will give us a trivial membership oracle. So we can just ignore the structure and use the randomized algorithm which I just mentioned. But what about deterministic algorithms? So there exist algorithms for general polytopes by Barwinock and Lawrence, but these are exponential time algorithms. But in fact, they are exact algorithms, not approximate algorithms, which achieve exponentially small error. So now the question is, we can't do anything for general polytopes yet. So the question is, can we somehow can we work with nicer polytopes? So for example, we have polytopes which have an underlying combinatorial structure. So for example, the independent set or the matching or the hypergraph matching polytope. Can we somehow leverage this combinatorial structure to get fast deterministic algorithms? So in recent times, there has been work in this area, starting with what is called a fractional independent set polytope. So here we have the normal independent set polytope, but we relax its constraints, and We also make the domain to be um, the solid cube. In fact, we'll consider what is called the truncated fractional independent set polytope. So here we even go further and restrict the variables to the interval 0 comma half plus delta. And for this problem, Gamarnik and for the computation of the volume of this polytope, Gamarnik and Smedera gave deterministic quasi-polynomial time algorithms. And the truncation interval they got was 0 comma half plus constant over maximum degree squared. The technique that they used was correlation decay, while Banks and Rex made more progress on this question. They gave an FP task, and the truncation interval was 0 comma half plus constant over maximum degree. The technique that they used was Barwinock's polynomial interpolation method. So in our work, we study the fractional matching polytope, which is the natural dual of this independent set polytope. This is defined as follows. So we now have variables on each edge. The constraints are at each vertex. All the variables that are incident on a vertex should sum up to less than or equal to 1, and the variables take values between this on the solid cube. So why is this interesting? Well, because the volume of the polytope and its dual can be quite different. So the fact that there's an algorithm for the fractional independent set polytope does not directly give us an algorithm for the fractional matching polytope. In fact, we'll consider the truncated version of this fractional matching polytope. So here we restrict the variables to the interval 0 comma 1 plus delta to the over the maximum degree. Just to note that this truncation interval is 1 plus it's a multiplicative relaxation of the trivial truncation interval, and trivial is 0 to 1 over maximum degree. For this interval, all the constraints are satisfied, so the polytope is just the e-dimensional cube for which volume computation is easy. So this is just some notation for later. I just mentioned that there's constraints which have to be satisfied at every vertex, so the volume can be written in this form. So this is our main theorem for the computation of the volume of the truncated fractional matching polytope. We show that for any graph G that has maximum degree capital delta and truncation parameter less than or equal to constant over maximum degree, we can have an FP task for computation of the volume. If we were to just use Banks and Rex, this result would give us a worse truncation parameter of constant over maximum degree squared. The technique that we use is cluster expansion. And to understand that, we'll have to talk about what are called polymer models. So here we're given a finite ground set P, whose elements are polymers. And this finite set is also endowed with a symmetric and reflexive relation that assigns incompatibility between any two polymers. There's also a weight function that assigns a weight to each polymer. And once we have this, we can write down the partition function of this polymer model. There's also what is called the cluster expansion. So it's defined as follows. Here, it's the infinite power series that's written here. And crucially, just note that the sum is over sets of polymers, special sets of polymers called clusters. And why is this useful? Well, because we have this Kodesky-Press criterion, which says that if we have a nice decay function supported on the polymers and the weights satisfy this inequality, then the cluster expansion, which we just saw, it converges absolutely. And when it comes to algorithms, we can use this to get an FP task for the problem of approximating the partition function of this polymer model. This is done by This is done by this was shown by Jensen, Kivas, and Perkins. And just a note that the most important condition here is to show that the Koteski press criterion is satisfied. The first two conditions are fairly easy to show. They essentially say that the weights of some polymers can be computed fast. So another thing to note is that the proof of Jensen, Kivas, and Perkins uses the Barwinock's polynomial interpolation method crucially. So let's now look at let's come back to the volume question. So our key insight is that the volume can be written down as the polymer model partition function. And here our polymers are induced subgraphs of the input graph which are connected. Our incompatibility relation is the distance to polymer distance in the graph. Two polymers are incompatible if their distance is less than or equal to 1. We also have this corresponding weight for each polymer. So now we can talk about the proof sketch. I'll just try to give you an intuition. So we just saw that our polymers are induced subgraphs of the graph which are connected, of the input graph which are connected. So each polymer encodes a connected component of violated constraints. So if we have the Koteski press criterion being satisfied, then it's essentially saying that the weight of the polymers decay rapidly. And this also implies that this will imply that the log of the partition function converges. And then we have the JKP algorithm, which can use this conversion to give us an algorithm, and it does it by the polynomial interpolation method. It's going to truncate the partition function up to the first log many terms and give us a good approximation deterministically. JKP also requires some weights of some polymers to be computed efficiently. And as I said, this is fairly easy to verify. So let's focus on, let me also give you a high-level sketch of verifying the Koteski press criterion, which I said is the most important condition. So here we view the polymer weight as the probability of the constraints being violated. And once we have that, we can pick a maximal independent set on the vertices. So sets of constraints become independent. And we can write the joint probability as a product of individual probabilities. And then our truncation interval being small will imply that we can bound each of these individual probabilities. And essentially, we are saying that the probability of violation of a set of constraints decays exponentially in the size of the constraint. So again, this is our main theorem for computing the volume of the truncated fractional matching polytope. We also extend this to the hypergraph, the computation of the volume of the hypergraph matching polytope. So here we're given a hypergraph with maximum degree capital delta and maximum hyperedge size k. We can just use the similar polymer model like in the graph case. We would get this weaker result. So let's just focus on the truncation parameter here. So we get that the truncation parameter is 1 over delta times k to the power k. But we show that we can get an exponential improvement over this truncation parameter. And this is written in the theorem mentioned here. So this is done by carefully working with the hypergraph structure, not just using the polymer models for the graph, similar polymer models like in the graph case. So our polymers will now be minimal connected subgraphs in the incident graph of H. And the analysis will use a combination of our cluster expansion technique with that of Banks and Rex. And to verify the Koteski-Prius criterion, it will require a hypergraph generation of the broken circuit theory for graphs, which we prove. So in summary, we showed that deterministic volume approximation can be done for the truncation of the fractional matching polytope, which is the natural dual of the independent set polytope. Our technique is cluster expansion. And we also develop an FP test for the truncation of the hypergraph matching polytope. And here we used a novel generalization of the broken circuit theory for hypergraphs. So as for open questions in future directions, so can we get a faster FP test? So currently the running time of our algorithm comes from the running time of JKP. Can we improve it to a function of delta times n to the c for some c? Can we get a bigger truncation interval? Maybe something like 0 to 1 minus epsilon for some small epsilon. And finally, can we relax the constant degree assumption? Maybe we can work with special class of graphs like expander, random, or bipartite graphs, where cluster expansion has been shown to go beyond this constant degree assumption. Okay, so that's all. And thanks for coming to the talk.